In the vast expanse of the universe, where distant stars flicker like embers in eternal darkness, humanity's desire to conquer interstellar space has long burned as a persistent flame in the collective mind, a primordial dream forged from nights spent gazing at the star-filled sky. Yet, as modern science casts its illuminating light on this aspiration, the veil of romantic mystery is gradually lifted, revealing formidable barriers in physics, engineering, and biology that appear insurmountable, prompting the profound question: is travel between the stars, the exploration of distant galaxies, forever merely an alluring fantasy? To address this inquiry, one must delve deeply into the fundamental laws of physics, examine the harsh constraints of cosmic biology, and assess the technological advancements reshaping our capabilities, commencing with the most solid foundation, Albert Einstein's theory of relativity. The notion of traversing galactic distances measures that even light, the swiftest entity known, requires tens of thousands, or even millions, of years to cover, immediately confronts the light speed barrier. According to the special theory of relativity, as a massive object approaches the speed of light, approximately 299,792,458 meters per second in a vacuum, its relativistic mass escalates toward infinity, necessitating infinite energy for further acceleration. This is not merely a technical limitation, it constitutes a core principle of nature. A spacecraft carrying a crew, even if only a micrometer in volume, would demand energy surpassing the total output of the Sun over its entire lifetime to attain 99.999% of the speed of light. For instance, dispatching an uncrewed probe to Proxima Centauri, the nearest star at about 4.24 light-years away, at 10% of the speed of light, 0.1 times the speed of light, would require energy equivalent to approximately 1.5 times 10 to the power of 17 joules, an enormous figure yet conceivable when compared to advanced nuclear fusion sources. However, achieving 90% of the speed of light escalates this exponentially, exceeding the combined energy reserves of human civilization, underscoring that conventional acceleration is futile. The challenges of time and space intensify when considering true interstellar distances. Even disregarding energy hurdles, journeying to neighboring galaxies like Andromeda, approximately 2.537 million light-years from Earth, using current chemical rocket technology, with maximum velocities around 11 km per second, the Parker Solar Probe's record, at about 0.000037 times the speed of light, would demand over 40 billion years. This duration surpasses the universe's age, about 13.8 billion years. This emphasizes that, if interstellar travel is feasible, it must rely on bending space-time or discovering metaphysical shortcuts, rather than simply accelerating faster. In pursuing such shortcuts, theoretical physicists have drawn upon the general theory of relativity, which depicts gravity as the curvature of space-time induced by mass and energy. From Einstein's equations, concepts of gravitational distortion have opened doors to mathematically exotic yet valid solutions, most notably wormholes, or Einstein-Rosen bridges. Mathematically, a wormhole forms a tunnel linking two disparate points in space-time, enabling instantaneous or near-instantaneous transit between locations billions of light-years apart. This paradigm shift redefines distance. Instead of navigating three-dimensional space, travelers tunnel through a higher dimension or a shortened space-time curve. Nevertheless, the physical viability of wormholes faces daunting obstacles. Mathematical models indicate that stabilizing a wormhole sufficiently open for a spacecraft to pass without immediate crushing by infinite gravity requires exotic matter, material with negative energy density, turned exotic matter. This exotic matter violates standard energy conditions, such as the weak energy condition or average energy condition, foundational to classical and relativistic physics. Simply put, ordinary matter possesses positive or zero energy. Negative energy essentially creates a region with less energy than the surrounding vacuum, exerting a repulsive force against gravity. While quantum mechanics permits localized negative energy via effects like the Casimir effect, where two closely placed metal plates in a vacuum exhibit lower energy than the ambient vacuum due to restricted virtual wave modes, the scale and sustainability of negative energy needed to stabilize a traversable wormhole, demanding negative energy equivalent to a planet's or star's mass, remain beyond current observational or experimental capabilities. Recent studies, such as those by Kip Thorne and collaborators, reveal that even with exotic matter, maintaining a wormhole might generate unstable quantum feedback loops, potentially destroying the structure upon formation, an effect tied to quantum field interactions in curved spacetime. Parallel to wormholes, a less fundamentally controversial yet technically formidable idea is the warp drive engine, popularized by the Alcubierre drive. In 1994, Miguel Alcubierre proposed a solution allowing spacecraft to exceed light speed without locally violating the special theory of relativity. Rather than propelling the ship through space, the Alcubierre drive contracts space ahead of the vessel and expands it behind. The spacecraft resides in a local warp bubble, remaining stationary relative to its immediate space, thus adhering to the local light speed limit. Theoretically, this permits effective velocities far surpassing light speed. However, the fatal flaw persists: the requirement for exotic matter. Creating the forward space contraction demands a negative energy density region. Subsequent analyses show that, even if exotic matter were available, forming and controlling the warp bubble necessitates immense fluctuating energy and precise distribution. Research in 2018 by Harold White at NASA's Advanced Propulsion Physics Laboratory, Eagle Works, suggested modified models to mitigate energy needs by altering the bubble's shape, for example, using a toroidal form, but even optimistic versions require energy equivalent to Jupiter's mass to propel a small ship at 10 times light speed. Moreover, a horrifying issue has emerged: warp bubble formation could produce intense Hawking-like radiation at the bubble's front edge, where virtual particles are torn from the vacuum. Upon halting, this accumulated energy would release as a devastating gamma-ray burst, annihilating everything ahead, transforming interstellar travel into planetary warfare. This is not merely a risk, it is an inevitable consequence of the original Alcubierre formulation. Thus, if overcoming the light speed barrier or bending spacetime via mechanisms requiring exotic matter, whose stable existence remains a major question in experimental physics, proves impossible, the sole remaining hope lies in maximizing near-light speeds, confronting the severe limits of biology and long-duration engineering. The biological challenges: the degradation of living bodies. Assuming a propulsion engine capable of reaching 0.5 or 0.9 times light speed, the next hurdle is whether living organisms, particularly humans, can survive such environments. Even overlooking psychological isolation over decades, the physical threats to the human body are profoundly serious. First is cosmic radiation. Beyond Earth's magnetosphere and magnetic field protection, astronauts face galactic cosmic rays and solar energetic particles. Galactic cosmic rays consist of high-energy subatomic particles, primarily protons and heavy atomic nuclei, traveling near light speed. Upon colliding with the ship or, worse, living tissue, they generate secondary particle showers, such as neutrons and pions, through strong nuclear interactions. Data from NASA's Mars mission studies indicate that cumulative radiation in long-term interstellar voyages, even with shielding, would exceed lifetime safety limits. Radiation dosage is measured in sieverts. An astronaut on the International Space Station receives about 0.5 sieverts annually. For a decades-long interstellar mission, this accumulates to tens of sieverts, causing irreparable damage. This radiation not only induces cancer but directly harms the central nervous system. Animal model studies demonstrate high doses lead to severe cognitive decline, irreversible memory loss, and behavioral changes. Mitigation requires dense shielding, using high-density materials like hydrogen-rich polyethylene or thick metal layers such as aluminum or lead. However, thickening shielding escalates ship mass astronomically, demanding even greater propulsion energy for desired speeds, creating a deadly engineering cycle. Second is the time dilation effect from the special theory of relativity. This is a double-edged sword. For a crew on a near-light-speed ship, time passes slower than on Earth. For example, a journey to a star 100 light-years away at 99% light speed would take about 14 years for the crew. This offers an apparent benefit. However, upon return or data transmission to Earth, they would discover over 200 years had elapsed on Earth. The entire known civilization would vanish, with families, friends, and nations possibly extinct. This is a permanent displacement from one's homeland. High relativistic interstellar travel equates to voyaging into Earth's future, an irreversible severance, rendering astronauts adrift survivors in an alien era. To surmount these biological and temporal barriers, scientists have conceived generation ships or life suspension methods. Generation ships are colossal self-sustaining cities designed to support a population large enough for journeys spanning hundreds or thousands of years, with descendants born, raised, and dying aboard, hoping the final generation reaches the destination. Such projects face unparalleled social and ecological challenges. Prolonged isolation, genetic diversity shortages, risking inbreeding over generations, and societal structure collapse, as observed in Earth's small isolation experiments, like Biosphere 2's ecological balance difficulties, pose major threats. Simulations of closed systems reveal the fragile equilibrium between oxygen, carbon dioxide, waste, and food production demands constant monitoring, a daunting task for uninterrupted multi-generational operation. Furthermore, transmitting the mission's core objective across centuries of cultural and linguistic evolution is a social engineering issue, not propulsion. The second approach, life suspension, hibernation or torpor, assumes halting or slowing human metabolism. While animals like bears naturally achieve this via body temperature drops and reduced oxygen consumption without significant harm, applying it to complex mammals like humans is another challenge. Current cryonics research focuses on metabolic slowing by cooling bodies near freezing, using cryoprotectants to prevent sharp ice crystal formation that destroys cells. However, experiments on complex organs still encounter severe issues with cryoprotectant toxicity, damaging cell membranes, and preserving neural synapse integrity in the brain. If perfect neuronal preservation fails, even after 500 years, astronauts might awaken in vegetative states or with irreparable cognitive deficits, dooming the mission. Overcoming propulsion limits, hypothetical engines. If humans cannot endure long, slow journeys, and space-time cannot be bent, a propulsion technology leap is essential to reduce travel time below a century, allowing one generation to survive and complete the voyage. Antimatter stands as the prime candidate for high-efficiency propulsion, harnessing Einstein's energy-mass equivalence absolutely. When a matter particle collides with its antimatter counterpart, e.g., a proton with an antiproton, their entire mass converts to pure energy as gamma rays and other particles, with 100% efficiency, far surpassing fusion, a few percent, or fission. To propel a 1,000-ton spacecraft to Proxima Centauri in 40 years, at average 10% light speed, estimates suggest about 300 tons of antimatter, and corresponding matter for reaction. The issue is not efficiency but production and storage. Currently, the world's largest particle accelerators produce antimatter in nanomicrogram quantities at immense energy costs. Producing hundreds of tons would require planetary-scale facilities consuming more than global energy use. Storage demands ultra-strong electromagnetic traps, like scaled penning or Paul traps, to prevent antimatter ship contact and annihilation. Any magnetic field failure would instantly destroy the vessel. Fusion confinement reaction engines, fusion designs promise significantly higher efficiency than chemical rockets, e.g., the Orion engine using nuclear explosions for impulses. Advanced fusion concepts, like magnetic or inertial confinement engines, could achieve higher exhaust velocities. Yet, even sustaining stable fusion in a continuous propulsion engine and attaining needed thrust, we remain limited by reaction plasma's maximum escape speed, typically a few percent of light speed. This means trips to nearest stars still span hundreds of years, reverting to biological and temporal challenges. Laser light sail engines, the breakthrough Starshot project exemplifies an alternative, carrying no propulsion fuel, only heat, and light pressure-resistant materials. The concept uses an Earth or orbit-based gigawatt laser array to beam onto an ultra-thin, ultralight sail of graphene or silicon nitride. With a 100 gigawatt laser array and a few gram sail, the craft could reach 20% light speed in minutes, cutting Proxima Centauri transit to about 20 years. This represents the foremost current achievement for uncrewed interstellar travel. However, for crewed ships, needing millions of tons for radiation shielding, life support, and mothership, required laser power becomes inconceivable, exceeding humanity's total energy output manifold, and the ship must carry complex shielding and support systems, multiplying mass and diminishing sail efficiency to infeasibility. Recent updates from 2025 indicate that breakthrough Starshot, despite initial promise, has faced significant setbacks. Reports suggest the project is on indefinite hold, with expenditures totaling less than $10 million from an pledged $100 million, highlighting funding and technical hurdles in scaling laser propulsion for practical deployment. Nevertheless, new designs in 2025 propose AI-optimized, potato-shaped light sails that could enhance efficiency, potentially enabling probes to reach Alpha Centauri in 20 years. The perceptual and millennial barriers. Even if technical means emerge, perceptual barriers regarding time and civilization's endurance divert all plans. Astronomers and cosmic philosophers often invoke the Fermi paradox: given the universe's vastness and antiquity, why no evidence of other civilizations? A compelling response is the Great Filter. The Great Filter is an evolutionary or technical barrier a civilization must surpass for interstellar capability. If behind us, in interstellar travel or long-term survival, most intelligent civilizations self-destruct or are physics-bound before galactic conquest. The discussed barriers, antimatter energy demands, exotic matter reliance for wormholes and warp drives, or crew degradation in long voyages, may embody these filters. If physical, light speed inviolable for massive matter, interstellar travel is illusory. If biological or social, no civilization maintains unity and purpose over millennia. Generation ships are societal gambles. Assuming generation ships, implementation spans thousands of years. Can an artificial social structure preserve initial objectives amid cultural shifts, internal conflicts, linguistic evolution, or technological obsolescence relative to other civilizations, if existent? Goal drift poses a major issue in long-term autonomous systems. Earth's isolation studies, even in controlled settings like Biosphere 2, show rapid atmospheric imbalances and complex social failures. A millennial project is more philosophical wager than engineering endeavor, requiring absolute consensus across dozens of generations without success evidence. Exploring theoretical escapes, modern physics incomplete. Though current physics imposes seemingly unbreakable limits, interstellar travel hope often rests on deeper universe insights yet ungrasped. String theory and extra dimensions, string theory and extensions, like M-theory, posit the universe exceeds our familiar for space-time dimensions. These extra-spatial dimensions are theorized as compactified at Planck scales, about 1/10 to the -35 meters. If accessible or manipulable, requiring energy beyond imagination to excite at that scale, they might offer another shortcut. Theoretically, an extra dimension could allow an object to leak across vast distances without traversing ordinary three-dimensional space, akin to an ant circling a hose rather than crawling its length. However, no experimental evidence suggests these dimensions can be activated or interacted with, and if existent, they seem locked at scales too minute for galactic travel impact. Quantum gravity and loop quantum gravity, both general relativity, continuous spacetime, and quantum mechanics, fundamental interactions, are incompatible, especially at singularities, inside black holes or the Big Bang. A complete quantum gravity theory might alter our spacetime nature understanding at minuscule scales. If spacetime comprises discrete quantum loops, fundamental structures might permit jumps between spacetime points. Yet, these theories remain nascent and offer no feasible travel mechanisms. Concepts of alternate universes existence. If star travel is too arduous in our universe, with light speed limit, could we shift to parallel universes? The multiverse concept, though controversial, arises naturally in cosmological models like eternal inflation, where alternate universe bubbles continually form. Transitioning to a universe with different physical constants, perhaps lacking light speed limit or allowing faster travel, would replace interstellar with inter-universal travel. But detecting, communicating, and traversing universes demands physics beyond the standard model and lies outside current technological predictions. If a true escape exists, it may involve manipulating dimensions or fundamental constants, not merely enhancing propulsion. Minimal travel techniques, practical applications in the 21st century. While above solutions remain pure science fiction, evaluating achievable steps in coming decades is crucial, as small advances may lead to greater leaps. Current space programs focus on mastering advanced propulsion, mainly high-efficiency but low-thrust engines. Solar electric and ion engines are under intensive study, using solar power to accelerate propellants at high exhaust velocities, achieving velocity ratios to light speed far greater than chemical rockets, though thrust is minimal. These suit solar system missions spanning decades but insufficient to meaningfully shorten nearest star flights within human lifespans. For near-interstellar travel, high-impulse backups like laser sails, Starshot, are most seriously considered, as they avoid basic energy law violations and can attain notable speeds within a project lifetime. If Starshot succeeds in dispatching sensors to Proxima Centauri in 20 years, it would yield invaluable data on a potentially habitable planet, Proxima b, marking the end of robot exploration confined to the solar system and ushering interstellar uncrewed probing. However, this is not crewed travel. Achieving crewed goals requires colossal energy sources humanity can currently harvest only from stars. In 2025, NASA's Interstellar Mapping and Acceleration Probe, launched in September, is advancing our understanding of interstellar boundaries by studying solar-wind interactions with interstellar medium, providing data that could inform future propulsion designs. Additionally, observations of interstellar comets like 3I/Atlas by multiple NASA missions offer insights into extraterrestrial materials, potentially aiding material science for long-duration crafts. Comparing with Earth travel means. To quantify interstellar travel's difficulty, compare it to humanity's Earth traversal history. The greatest conquered distance is across oceans. Columbus took months to cross the Atlantic, about 5,000 kilometers. With average speeds, humans reduced intercontinental travel from years to hours, via jet aircraft. This progress stemmed from denser energy sources, petroleum, jets, and efficient operations, aerodynamics. The distance to Proxima Centauri is 4.01 times 10 to the 13 kilometers. Reducing travel time from 75,000 years, using Voyager 1 at 17 kilometers per second, to 20 years, Starshot equates to shrinking Atlantic crossing from 6 months to about 1.5 seconds. The scale disparity is absurd. It demands a paradigm shift in physics and engineering, not linear improvement. The role of artificial intelligence in the interstellar era. If biological and social barriers of long voyages cannot be overcome, and physical solutions, wormholes, warp drives, require non-existent matter, humanity's sole remaining hope for expansion is replacing humans with non-biological entities, superintelligent artificial intelligence. If embracing generation ships, maintaining objectives, and social stability over thousands of years is nearly impossible for brains evolved for short-term problems, decades. However, superintelligent artificial intelligence designed for interstellar tasks can transcend these. Artificial intelligence is unaffected by boredom, generational conflicts, or cultural goal shifts. It can sustain motivation, self-repair, continuously optimize closed ecosystems on motherships over millennia, and make optimal decisions from accumulated data. Artificial intelligence could conduct exploration, establish automated outposts, and transmit information, or digitized human brain maps, back to Earth for guidance. In this scenario, interstellar travel ceases as human journeying, becoming the propagation of humanity's consciousness or code. Advancements in 2025 highlight artificial intelligence's growing role in space. NASA's partnerships are using artificial intelligence to predict solar events, enhancing mission safety. Moreover, artificial intelligence has enabled the most detailed Milky Way simulation, mapping 100 billion stars, aiding navigation for future probes. Projections indicate the artificial intelligence in space exploration market will grow from $6.7 billion in 2025 to $57.9 billion by 2034. Underscoring its pivotal function in overcoming interstellar challenges. Recent breakthroughs in warp drive and wormhole research. In 2025, significant strides in warp drive theory have reignited optimism. Researchers have proposed models realizing warp drives without negative energy, using positive energy distributions and subliminal speeds, potentially making them physically viable. Some experts suggest warp drives or equivalents could emerge within 100 years, driven by advances in quantum fields and energy manipulation. Experimental efforts, like those at the ZC Institute, are testing pulsed warp bubbles with compact fusion power, bridging theory and practice. Wormhole research has also advanced. Studies describe long, bumpy caterpillar-like wormholes connecting black holes, mapping shared interiors theoretically. PT-symmetric wormholes with negative energy are being characterized, detectable via gravitational wave echoes. Speculative detections of signals from parallel universes through brief wormhole openings have sparked debates on multiverse. Updates on biological research for space travel. 2025 has seen focused experiments on spaceflight's biological effects. Mission sending worms to the International Space Station in 2026 aim to study microgravity's impacts on muscles, bones, and vision, informing human adaptations. Research indicates re-engineering human bodies for space, addressing reproduction uncertainties off Earth. Spaceflight activates the dark genome in human cells, accelerating aging in stem cells, highlighting needs for countermeasures. Progress in antimatter propulsion. Antimatter research in 2025 outlines roadmaps for engines 300 times stronger than chemical ones, potentially reaching Proxima Centauri swiftly. Though production remains challenging, theoretical efficiencies promise transformation, with energy from 1 gram equaling vast rocket fuel amounts. Conclusion: between fantasy and feasibility. Thus, is travel between stars merely an illusion? The answer is nuanced. Crude interstellar travel at near-light speeds or via space-time shortcuts, wormholes, warp drives, remains illusory under current physics comprehension. Energy conservation laws and negative energy necessities are seemingly inviolable barriers. However, robotic interstellar travel using light pressure techniques, laser sails, or high-energy propulsion, antimatter, aiming for 20% light speed and mission completion in decades, may materialize within a century, provided large-scale energy production and antimatter storage resolve. This is not humanity's migration dream but scientific presence expansion. If humanity cannot address fundamental physics issues, like stable exotic matter for space-time bending, star travel will forever reside in captivating imagination, a reminder of the universe's immensity and terrifying limits. Future developments hinge on physicists finding loopholes in the Standard Model or general relativity, loopholes enabling shortcuts without breaching verified principles at explored energy levels. Until then, stars remain distant beacons, beautiful yet untouchable, and dreams of intergalactic voyages persist as our grandest illusion.